A battery stores electricity. Everybody knows that. A battery, you plug something in, it charges up, and it stores the electricity for later. You carry it around in your pocket, and when you need the electricity, it gives it back. Simple. I mean, what else would a battery do? The whole word battery makes you think of a little container, like a jar. Benjamin Franklin even called it that. He had a bunch of Leyden jars lined up, charged them all at once, and said that's a battery, like a battery of cannons. A row of things all doing the same job. So we've had this picture for over 200 years. The battery is a container for electricity. And I want you to sit with that for a second, because it makes perfect sense. You charge a battery. You discharge a battery. Charge goes in, charge comes out. What more is there to say? That picture is completely wrong, and I can prove it. See, I love this particular mistake because it's not a lazy mistake. It's a very intelligent mistake. It's the kind of mistake that reasonable people make when they take the language at face value and never bother to open the box and look inside. And what's inside a battery is so much stranger, so much more interesting, so much more beautiful than a jar of stored up electricity. What's actually happening in there is a kind of controlled chemical war. Atoms ripping electrons off other atoms, metals dissolving, new substances forming, a restless, violent molecular drama that just happens to push electrons through your flashlight bulb on the way by. But I'm getting ahead of myself. Let me take you through this properly. Let me first show you why the container idea feels so right. Then I'll show you exactly where it falls apart. And then we'll build up the real picture from scratch, atom by atom, until you see what a battery actually is. And I think when we're done, you'll never look at one the same way. All right. So why does the container picture feel right? Because everything we do with batteries sounds like filling and emptying a bucket. You charge your phone, you drain the battery. It's at 50%. It's full. It's dead. Every single word we use reinforces this idea that there's a fixed quantity of electricity sloshing around in there and we just top it off when it gets low. And it goes deeper than just language. Think about how you experience a battery in real life. You pull one out of a charger, it's warm, something happened in there. You stick it in a toy, the toy runs, you use it all day, and eventually the toy slows down and stops. Everything about this experience screams container. Something was full, now it's empty. The container story works perfectly at the level of daily experience. Even the way we measure batteries reinforces the myth. Milliamp hours. That's the rating you see printed on the side. Amps are a measure of electrical current. Hours are a measure of time. Multiply them and you get a quantity of charge. So the battery holds a certain quantity of charge, right? Like a water tank holds a certain number of gallons. And if you're a person who knows a little bit of physics, you might dress it up more formally. You might say, well, a battery stores electrical energy. And that sounds very scientific. Energy is a real thing. Electrical energy is a real thing. So the battery stores electrical energy. Done. Let me tell you something. That I have a great respect for wrong ideas that feel right, because they tell you something about how the human mind works. The container metaphor isn't just a casual mistake. It's a deeply appealing story that maps perfectly onto our everyday experience. And that makes it very hard to dislodge. You almost have to sneak up on it. So let's be more careful. What does that actually mean? Stores electrical energy. Electrical energy is the energy associated with electric charges in motion or in position. Charges flowing through a wire. That's electrical energy. A static charge sitting on a surface. That has electrical potential energy because of where it is relative to other charges. So is there some enormous pile of charge just sitting inside the battery straining to get out? No. And this is the first crack in the picture. A fully charged battery has almost exactly the same total electric charge inside it as a dead battery. Count up all the positive charges and all the negative charges inside a fresh AA cell. Now count them up in a dead one. The numbers are essentially the same. There's no extra electricity in the charged one. There's no missing electricity in the dead one. That should bother you. If a battery stored electricity the way a bucket stores water, then a full battery would have more charge in it than an empty battery. It doesn't. The charge doesn't change. I'll say that again because it's important. Go to the store. Buy 2 identical batteries. Leave one in the package. Put the other in a flashlight and run it till the light goes out. Now weigh them both. You'll notice the dead battery weighs almost exactly the same as the fresh one. Actually, if you had a sensitive enough scale, you might detect a tiny, tiny difference. But that's due to mass lost through leaking gases, not missing electrons. The electrons are all still in there. Every single one. They didn't leave and not come back. Electrons flow through the circuit and return to the battery. They go out the negative terminal through your device and come back in through the positive terminal. It's a complete loop. Electrons are not consumed. They are not fuel. They are the conveyor belt, not the cargo. So what changes? This is the question. This is the door. And once you walk through it, you end up somewhere completely different from where you expected. Let me tell you what's actually in a battery. I'll use an ordinary alkaline battery, the kind you buy at the store, the kind you put in a flashlight or a remote control. You crack one open and you don't find a little tank of electricity. You find chemistry, wet, messy, reactive chemistry. And by the way, please don't actually crack one open. They're not dangerous like some batteries, but the potassium hydroxide inside is caustic. It'll irritate your skin. I'm describing this so you can picture it, not so you do it. On one side, you've got a metal called zinc, ground up into a paste, actually, mixed with a thick alkaline gel, which is basically a very concentrated solution of potassium hydroxide. They call it alkaline because the electrolyte is alkaline, meaning its pH is high, meaning it's basic rather than acidic. That's the negative end, the anode as they call it. Anode is a Greek-derived word that roughly means the way up, which is the direction that positive current was thought to flow. The terminology is a bit confusing, frankly, because the electrons flow out of the anode, which seems like it should be the negative terminal, and it is. But the naming convention refers to conventional current, which flows in the opposite direction. Don't worry too much about the names, focus on the physics. On the other side, you've got a different substance, manganese dioxide, a dark, powdery compound. That's the positive end, the cathode. And sitting between them is that alkaline gel, the electrolyte, soaking through a thin separator that keeps the two sides from touching directly. That separator is important. It lets certain particles through, but keeps the metals apart, like a wall with tiny doors. Now, here is the key idea, and I want you to pay very close attention to this because this is where the whole picture changes. The zinc atoms want to react with the alkaline electrolyte. They have a powerful chemical tendency to give up electrons. Not because someone is forcing them, not because there's an electric field making them do it. They want to do this. It's energetically favorable. The zinc atoms are in a high-energy chemical state, and they can reach a lower energy state by releasing electrons. Think about a ball sitting on top of a hill. Nobody has to push it. It rolls down because that's the direction of lower energy. Zinc atoms in an alkaline solution are like balls on top of a chemical hill. They want to come down. So each zinc atom releases 2 electrons and becomes a zinc ion, which dissolves into the electrolyte. The electrons are left behind, sitting on the zinc electrode. They've got nowhere to go inside the battery because that separator won't let electrons through. Electrons can't swim through the electrolyte. Only ions can move through the liquid. So the electrons pile up on the zinc side, which is why we call that the negative terminal. It's got a surplus of electrons. And I want you to picture this at the atomic scale because it's really quite dramatic. Imagine you're standing on the surface of the zinc electrode, watching. It's a metallic landscape, a lattice of zinc atoms all neatly arranged. And then the alkaline solution washes over and the atoms at the surface start to tremble. One by one, they let go of 2 electrons each, and they detach from the lattice like tiles peeling off a wall. They float away into the liquid as positively charged zinc ions, leaving behind a surface that's now bristling with orphaned electrons. Millions of atoms doing this simultaneously. The surface is eroding, but it's not random erosion like rust. It's organized. It's purposeful. Every atom that leaves sends its electrons toward the terminal. If you could hear it, I imagine it would sound like rain, a very faint, very rapid pattering, the sound of a metal slowly dissolving itself to generate a current. Over on the other side, the manganese dioxide has the opposite appetite. It desperately wants electrons. Its chemical structure can accommodate extra electrons very comfortably. It's like a valley at the bottom of a different chemical hill, waiting to catch whatever rolls down, but it can't get the electrons from the zinc directly because the separator and the electrolyte are in the way. Electrons don't travel through liquid electrolyte. Only ions do. So here's the trick. Here is the entire reason a battery works. If you connect a wire from the zinc side to the manganese dioxide side, on the outside the electrons finally have a path. They flow through the wire, through whatever device you've connected, through your flashlight bulb or your motor or your radio, and they arrive at the cathode where the manganese dioxide is waiting for them. The chemical reaction on each side can now proceed because the electrons have found a way to get from where they're produced to where they're consumed. And this is the critical insight. The energy was never electrical. The energy was chemical. It was stored in the arrangement of atoms, in the molecular structure of the zinc and the manganese dioxide, in the fact that these substances have not yet reacted with each other but very much want to. A battery is a chemical system held in a state of suspended reaction. The only thing preventing the reaction from completing is the absence of an external path for the electrons. You provide the path, the reaction proceeds, and the chemical energy gets converted into electrical energy as the electrons make their journey. That's a completely different story from a container of stored electricity, right? The electricity is not stored. The electricity is generated on demand by chemistry the moment you close the circuit. Let me put it another way. Imagine you've got two rooms separated by a wall. In one room, there's a tank of water on a high shelf. In the other room, there's an empty tank on the floor. You drill a hole through the wall and connect them with a pipe. Water flows from the high tank to the low tank, and on the way it turns a little water wheel and does useful work. Now, was the water stored in the pipe? No. Was the energy stored as moving water? No. The energy was gravitational potential energy. The water on the high shelf had energy because of its position. When it flowed down, that potential energy got converted into kinetic energy, which turned the wheel. The pipe didn't store anything. The pipe was just the path. A battery is the two tanks. The wire is the pipe. The electrons are the water. And the chemical reactions are gravity, the driving force that makes everything flow. The battery doesn't store the flow. It stores the potential, the chemical potential that creates the flow when you give it a path. But even this analogy has limits, and I want to point them out because learning where an analogy breaks down teaches you almost as much as the analogy itself. In the water analogy, the water in the high tank is the same water that flows through the pipe and ends up in the low tank. It just moved from one place to another. In a battery, the electrons that flow through the wire are not the same particles that carry charge through the electrolyte. Inside the battery, it's ions doing the moving. Outside, it's electrons. The identity of the charge carrier changes at the electrode boundary. That boundary, that interface between the solid metal and the liquid electrolyte, is where something genuinely extraordinary happens. It's where chemistry hands off to electricity, where one kind of particle stops and another takes over. Think of it like a relay race. The zinc atom runs the first leg. It hands off its two electrons at the electrode surface. The electrons sprint through the wire, doing useful work along the way. At the cathode, they arrive and hand off to the manganese dioxide, which finishes the race by completing its own chemical reaction. 3 different runners, one continuous race. But the baton, the energy, passes smoothly from one to the next. This relay nature is why batteries can be so efficient. There's very little energy lost at the handoff points if the chemistry is clean. The electrode surfaces are designed often at the nanometer level to make these transitions as smooth as possible. Material scientists spend years engineering the surface texture, the crystal orientation, the particle size of electrode materials, all to make that handoff happen faster and cleaner. Alright, so now you see the basic picture, but I want to go deeper. Because there's something really elegant happening at the boundary between the electrode and the electrolyte, at the surface where the metal meets the liquid, and it tells you a lot about how nature actually works. When that zinc atom gives up 2 electrons and becomes a zinc ion, it peels off the surface of the metal and dissolves into the electrolyte. It's now a positively charged particle floating in solution. Meanwhile, the 2 electrons it left behind are sitting on the metal electrode. So what happens right at the surface? You get a tiny separation of charge. Positive ions on the liquid side, excess electrons on the metal side, and this charge separation creates a voltage, an electric potential difference. This is where voltage comes from, not from some mysterious electrical pressure that was pumped in during charging. It comes from the chemistry. The tendency of zinc to dissolve and release electrons establishes an electric potential at one electrode. The tendency of manganese dioxide to grab electrons and react establishes a different potential at the other electrode. The voltage of the battery is the difference between these 2 chemical potentials. And here's the beautiful part. Every pair of materials gives you a different voltage. If you use zinc and manganese dioxide, you get about 1.5 volts. If you use lithium and cobalt oxide, you get about 3.7 volts. If you use lead and lead dioxide and sulfuric acid, you get about 2.1 volts. The voltage is not a property of the battery's size or shape. It's a property of the chemistry, of which atoms you picked and how badly they want to exchange electrons. That's why a tiny little watch battery and a fat flashlight cell can both be 1.5 volts. Voltage doesn't depend on how much stuff you have. It depends on what stuff you have. A drop of zinc next to a drop of manganese dioxide creates the same voltage as a kilogram of each. What changes with size is capacity, how long the battery can keep the reaction going before the reactants are used up. But the voltage, the pressure that pushes the electrons, is set by the atomic physics. You can actually predict the voltage. Chemists have a table called the electrochemical series that ranks metals and other substances by how strongly they want to release or grab electrons. It's like a league table for chemical greediness. At one end you've got lithium, which is incredibly eager to dump its electrons. At the other end you've got fluorine, which will grab an electron from almost anything. The farther apart two substances are on this table, the higher the voltage when you pair them. This is why lithium batteries have a higher voltage than alkaline batteries. Lithium sits much further up the table than zinc does. It has more chemical potential to give. So when you pair lithium with something like cobalt oxide, which is quite eager to receive, you get a bigger voltage gap, 3.7 volts instead of 1.5, not because lithium batteries are better engineered, but because the atoms themselves have more energetic distance between them. And this is testable in the simplest way. Stick a zinc plate and a copper plate into a lemon. Connect a wire between them and you'll measure about 9/10 of a volt. The citric acid in the lemon acts as the electrolyte. The zinc wants to dissolve. The copper doesn't. Electrons flow from zinc to copper through the wire. You've made a battery. A terrible one, but a battery. And the voltage you get, that 9/10 of a volt, is not determined by the size of the lemon or the size of the plates. It's determined by zinc and copper being a certain distance apart on the electrochemical series. You could use a watermelon or a grape. Same voltage. Different capacity, different internal resistance, but same voltage. I think this is remarkable. The voltage of a battery is determined at the atomic level.